I finally finished writing a scientific article that I've been thinking about for several years, and I decided it might be an idea to publish it. So I looked up on the internet some of the scientific journals that might be interested in publishing it for me. So I found one called the New Journal of Physics, I think it is, one of Institute of Physics's publications. And I thought, well, this sounds pretty good, so I'll upload the file and submit it. So I got through all this procedure of uploading the PDF file of the paper, and I put all my details in, and I got right to the bottom of the procedure, and it said there was a publication charge of 1,600 and something pounds. And I thought, you must be joking. They want me to pay them to publish my work. Well, anyway, okay, so there is a reason for this charge, because it's open access, which means that anyone can read it, anyone can download it and read it. So it would be a good place to publish my work, I thought. And then it goes on and it says this is peer review. It would be assessed for the quality and so on. And then I got to the point where I was thinking, well, actually, the peer review process would reject my paper in any case, because it's controversial and doesn't fit in with the current paradigm in physics. And it obviously wouldn't be published because it's not in the interests of the establishment to publish my work, especially as I'm completely unknown in the field of theoretical physics, gravitation and relativity. So I then carried on thinking about this. They even said in their blurb, you could make a video of your contribution in order to let other people see it and hear about it. And I thought, yes, I could make a video of my paper, and it's not going to cost me £1,600, and I can also publish my paper for nothing on one of the archive or Vixra, it's called. So I'm afraid I bypass firms like the Institute of Physics Publishing, and I prefer to do it my own way. And this video is about the paper I wrote, in which I'm going to describe what I want to say about black holes. The title of the paper is Have They Got It Wrong About Black Holes? By recognizing that Newtonian gravity is a manifestation of the time curvature in a four-dimensional Lorentzian manifold, as in Einstein's general relativity theory, it can be shown that space and time are completely regular in the neighbourhood of a static point mass, and that a black hole and event horizon are mathematical artefacts. Correctly interpreting Newton's law in conjunction with GR also leads to the conclusion that superluminal velocities do not occur, and that gravity does not diverge to infinity as masses approach each other, which also removes the physically inexplicable issue of a singularity in spacetime. 1. Introduction. Black holes play a central part in the current paradigm in cosmology and astrophysics, and are believed to be ubiquitous in the universe. The solution of Einstein's theory of general relativity for the curvature of spacetime near a point mass can be used to justify their prediction, and in the meantime, evidence for their existence has been claimed by means of two experimental techniques: gravitational wave signals and the so-called EHT telescope. However, looking back over the history of the subject, I am convinced that a crucial error was made that resulted in the concept of a black hole becoming falsely promoted. It is this theoretical aspect that I'm going to concern myself with in this paper. 2. Background theory. The first person to obtain a solution for the gravitational field outside a point mass using GR was Carl Schwarzschild in 1916, less than a year after Albert Einstein published his theory. A spacetime increment may be written in spherical polar coordinates t r theta phi as ds bar squared equals c squared dt dash squared equals ac squared dt squared minus b dr squared minus capital C d theta squared plus sine squared theta d phi squared, where capital A, B and C are radially dependent functions describing the curvature of the time, radial and angular metric coefficients respectively. C is the speed of light, dt dashed is an increment of proper time, dt is an increment of coordinate time, and dr is a radial increment. This is, I believe, the most general description for a spherically symmetrical space that must prevail in the neighbourhood of an isolated static point mass. However, as I should explain later, a different form for the metric is usually adopted, in which capital C is replaced by r squared, and r should then be construed as a different radial coordinate. Next, from the metric, the calculus of variations is used to obtain geodesic equations for the four variables, and one obtains what we see in equations 2. The equation of interest for describing the radial free fall of a test particle directly towards the mass at the origin is the second of these expressions, which leads to the following equation of motion for free fall, equation 3. Now, using the radial part of the metric in equation 1 to eliminate t dot, we can then reformulate equation 3 as equation 4. Einstein's field equations of GR enables us to find the way capital A, B and C relate to each other. Christoffel curvature coefficients are found from the geodesic equations and then used to obtain the Ricci tensor components R, A, B. The components that are not trivially zero are given in equation 5, with an equivalent equation to the third one for R phi phi. For the vacuum outside the point mass, the Ricci tensor components are set to 0 to satisfy Einstein's field equations of GR. Accordingly, we then obtain from equation 5 the following pair of simultaneous equations relating capital A, B and C. Equation 6. Since there are only two independent equations for the three functions, it means they cannot be solved explicitly without some additional condition or assumption. As mentioned, C is usually replaced by r squared, which in effect removes one of the unknowns and allows an exact solution to be obtained, with two unknowns and two simultaneous equations. The angular part of the metric then appears as it would be for a flat spatial metric, and A and B are constrained in some way to be related to each other. This procedure essentially amounts to introducing a new radial coordinate, and the coordinates are then called Schwarzschild coordinates, in honour of Schwarzschild's name. This new radial coordinate is not accurately the same as r in equation 1, but related to it via 2 pi times the circumference of a sphere of radius r centred at the origin. Equation 6 can then be solved exactly. They simplify to what we see in equation 7, which can now be solved to give A equals 1 over B equals 1 minus alpha over r, equation 8, where alpha is a constant of integration. To relate the geometry of GR expressed via the constant of integration alpha to real physical quantities, it is customary to make use of Newton's law of gravitation in what is called a weak field approximation. So inserting B equals 1 over A from equation 8 into the free fall equation of motion, equation 4, one then obtains r double dot plus A dashed c squared over 2 equals 0. And since A dashed equals alpha over r squared from equation 8, this appears to agree with the inverse square law behavior of Newton's law of gravitation, in which free fall acceleration is minus gm over r squared. And this gives alpha equals 2gm over c squared, which is a positive quantity known variously as the gravitational radius or Schwarzschild radius. This deduction is based on the tacit assumption here that we may compare or identify the proper acceleration in GR with the absolute acceleration in Newton's law. Alpha turns out to represent only a small distance, about 2.8 kilometers for a star, the mass of the Sun. The solution, as it has been interpreted, thus predicts that A and B change sign at a positive distance r equals alpha. For a point, or highly compacted mass with physical radius less than alpha, it therefore seems that a discontinuity occurs in spacetime, and this distance alpha has become known as the event horizon of a black hole. 3. Discussion and further theory. Historically, Schwarzschild recognized the presence of a mathematical discontinuity in his solution, but by defining a suitable auxiliary radial coordinate, he forced the discontinuity to be at the origin, since he believed it to be unphysical. Shortly afterwards, Droste and Weil provided a solution, but restricted the range of r to r greater than alpha. Subsequently, Hilbert extended Droste and Weil's solution to the region r less than alpha, on the grounds that a coordinate transformation does not alter the physics of the situation, and GR is supposed to be a generally covariant theory. It is essentially Hilbert's solution that allows for a change in sign of A and B that is accepted today. Throughout his life, Einstein himself considered the black hole solution to be unphysical, both because of the strange behavior near the event horizon and because there is a singularity at the center of the black hole. He was on a quest to find a unified theory that would eliminate the singularity in his theory of gravity. Other authors, such as Moffat, claim to have discovered exact, non-singular solutions of Einstein's field equations. For example, in Moffat's modified gravity theory, an exotic field energy is added that supposedly permeates all of spacetime and causes a negative force to be exerted on a collapsing star and prevents the formation of a black hole. However, I am convinced that there is a much simpler explanation that eliminates the irregular behavior of spacetime. It is clear to me that false thinking entered into the standard analysis many decades ago, as I shall now explain. Firstly, the geometry of Newton's inverse square law of gravitation is undeniably strictly Euclidean or flat. In other words, spatial curvature plays no part in Newtonian or classical gravity. On the other hand, Einstein's GR is a geometrical theory explaining gravity through the curvature of both space and time. Logically then, if we relate Newton's law with GR in any way, Newtonian gravity is that part of gravity resulting exclusively from the curvature of time. William Unruh puts it this way: gravity is the uneven running of clocks at different places. When comparing GR with Newtonian gravity, it is therefore incorrect to use the reciprocity of space and time curvature dictated by GR from equation 8, not even approximately. To compare GR with classical gravity, you have to write B equals 1 as for a Euclidean space, and then the equation of motion from equation 3 becomes r double dot plus a dash over 2a times c squared plus r dot squared equals 0, with b equals 1. Solving this differential equation and inserting Newtonian expressions for free fall acceleration and velocity then gives the following expression for A. A equals 1 plus alpha over r to the minus 1, where alpha is again 2gm over c squared. Thus we have quantified the insight that the gravitational force or acceleration in Newton's law relates strictly to the curvature of time in GR. Clearly, as shown in figure 1, the function A in equation 11, the regular solution in the figure, shows no discontinuity for any value of the radial coordinate r. Now writing the Schwarzschild radial coordinate in the GR solution of equation 8 as r star, so as not to confuse the two coordinates, we may write A equals 1 minus alpha over r star equals 1 plus alpha over r all to the minus 1, from which it follows that r star equals r plus alpha, a simple linear relationship. The difference is extremely small for r very much greater than alpha, and distinguishing between the two then becomes irrelevant. But when r becomes of the same order of alpha, the situation is crucially different. While the range of r goes from 0 to infinity, the range of r star is from alpha to infinity. The spacetime manifold, therefore, does not exist for r star less than alpha, and Hilbert's extension to r star less than alpha is therefore meaningless, and there is therefore no event horizon. Clearly, the solution A equals 1 plus alpha over r to the minus 1 with B equal 1 does not accurately satisfy Einstein's vacuum field equations of general relativity. However, we do not expect it to, and there is no requirement that it should, since Newtonian physics does not treat curved space per se. As stated, Newton's inverse square law of gravity describes that aspect of gravity caused exclusively by the curvature of the time coordinate, and this is manifestly dominant for most cases we consider, such as planetary motion. However, space curvature becomes significant when speeds approach the speed of light, and distances to the central mass become small, and this will modify gravity from being purely Newtonian. The use of general relativity is then to describe phenomena that Newton's law does not describe, such as the perihelion rotation of the planet Mercury and the bending of starlight passing near the Sun. To satisfy GR, we then require that B equals 1 over A, with C equal to R star squared. And this gives the following complete solution for the curvature of spacetime due to a static point mass. A equals 1 over B equals 1 plus alpha over r to the minus 1, and C equals r plus alpha squared. 4. A limiting velocity and gravitational force. Some further predictions are now apparent. By integrating equation 10, it is straightforward to show that the proper velocity of free fall is given by r dot squared over c squared equals 1 minus a, where the asymptotic condition a goes to 1 as r goes to infinity has been used. And then, with a equals 1 plus alpha over r to the minus 1, we have equation 15. This means we have r dot goes to c for r to naught, which contrasts fundamentally with the black hole solution where r dot equals c times the square root of alpha over r, which gives r dot goes to c for r goes to alpha, and r dot goes to infinity for r goes to 0. The solution presented here thus predicts a limiting free fall velocity of c, as in special relativity, which is much more intuitively acceptable than both the black hole solution, or Hilbert's extension, and Newton's law that both predict infinite speed as r goes to 0. Furthermore, the radial free-fall acceleration may be written as in equation 17, which shows classical Newtonian behavior for r very much greater than alpha, but decreases from inverse square law behavior for r of the order of alpha. If I define an effective gravitational mass ratio, m effective over m, as the acceleration in my model divided by the acceleration in Newton's law, we obtain that the m effective over m equals 1 plus alpha over r to the power minus 2. We thus have for large r, Newton's law being obeyed, i.e. that is, the effective gravitational mass is constant, as we would expect, but as r decreases to 0, the effective gravitational mass goes to 0 itself, and the singularity you expect to find at r equals 0, where the laws of physics would break down, disappears. 5. Conclusion. In conclusion, the deductions outlined here deviate from the current paradigm. The idea of a black hole and event horizon is a mathematical possibility, but it can be shown to be non-physical by correct interpretation of Newton's law in conjunction with Einstein's general relativity theory. The present model is much more intuitive and rules out superluminal velocities. Gravity does not diverge to infinity as masses approach each other, which removes the physically inexplicable issue of a singularity in space-time. It would be satisfying if existing observations and calculations of trajectories and images that have previously led to the alleged presence of black holes could be re-examined on the basis of the model presented here, where there is no event horizon or black hole.